So hello everyone, welcome to our channel Physics for AP. So in previous episode we have discussed about the plane surfaces, that is refractive index, the denser medium and rarer medium, the Snell's law, the application of total internal reflection and critical angle. And also we have seen an experiment about the rectangular glass slab. So now we will be going on to the curved surface. So in curved surface we will be discussing about the lenses and the types of lenses, the convex and concave lenses, and the ray diagrams, and also the uses of these lenses. So let's start what is meant by lens. We have two types of lenses, one is a convex and another is a concave lenses. So let us discuss these two in details. So as the lenses should be a transparent material, that means it should passes a light through it. So we can say the definition of the lens as it is a piece of a transparent material where the light passes through it and it has two curved surfaces which are bounded together is said to be called as a lens. So even our eye is also a lens which is called as a natural lens, and also we have an artificial lens also whenever we have a defect of it. So we can say the definition of the lens as a piece of a transparent material where two curved surfaces are bounded together. Now let us discuss about the convex lens. So convex lens are also called as the converging lens. So this is an image of a convex lens, so where the edges are thin and in the middle it is thick, where the optic center is present it is thick. So the convex lenses types we have as the double convex lens, which is also called as a biconvex lens, where we have two curved surfaces of a convex and middle we have a thick. Another one we have a plano-convex lens, one we have a plane surface, another we have a curved. Another one is a concavo-convex lens, so where we have at the middle it is thick and at the edges it is thin. So that is what we call concavo-convex. So when a parallel beam of light passes through the convex lens, so it converges and meet at a point called focus. So that is why it is said to be called as the converging lens. And what are the uses of the convex lens? So the convex lens are used as the optical instrument, where it is used in the telescopes. So in telescopes we use a convex lens to view the distant objects like the moon, and it is also used to view the celestial bodies, not only the moon, and it is used to magnify it little bit bigger one. So it is also used in the microscopes, where the microscopic objects it can be used to magnify with the help of the convex lens. And the lens which is present in our eye is also a convex lens, which is a natural convex lens. And also in the camera lenses, where we can focus of an object, and also the magnifying lens. So the magnifying lens which is kept near to an object, it magnifies and make it little bit bigger. So these are the uses of the convex lens. Another one is hyperopia or hypermetropia. So the defect who cannot see the near objects, that is when the light ray falls upon our eyeball, as we have a convex lens, they converges at beyond our retina. Now to correct this defect, the hypermetropia, we need a lens to make the point to be focused on the retina. So for that we use a convex lens. So where a parallel beam of light falls upon the convex lens, it converges and make it to fall upon the retina and makes the object to be seen clearly. And let us see about the concave lens. So concave lens is also called as a diverging lens, so where we have at the edges thick and the middle we have thin, that's near the optic center. And let us see the types of concave lenses. The first is double concave lens, or also called as biconcave, where we have thin in the middle. And another one is convexo-concave, where we have thin at the middle and thick at the edges. and another one is plano concave, where we have one surface as plane and other surface as concave. Now, why concave is called as a diverging? Why? Because when a parallel beam of light falls upon the concave lenses, it spread out. So that is why it is said to be called as a diverging lens. So the lines are being spreading out, so it is said to be called as diverging. Now let us see the uses concave lenses. One is it is used in the binoculars. So in the binoculars, to focus on an object, we use the binoculars to see the distant object, and also it is used to see in the telescopes. So in telescopes to see the celestial objects. So we use convex and concave also, and also it is used in eyeglasses, and also used in the flashlight to make the lines diverge, the light rays diverge. So we use a convex lens so that the light rays can spread out on the far distance over here. And it is also used to correct the defect of myopia, that means the person who cannot see the far objects. So as the focusing spot, the light focusing spots fall in front of the retina. Now to make it far, that is to make it behind, to make it fall upon the retina, we need a diverging lens so that it will diverge, that means it spread it out little bit far away and make it to fall on the retina. So for that we need a concave lens or biconcave lens, so that it gets diverged first, falls upon the convex lens and make it focus upon the retina over here. So it's also used as a correction of myopia over here. So we will be discussing about the defects of eye, that is about the hypermetropia and myopia, in the next video. So let's discuss in detail in the next video. Now let us see about the ray diagrams now. Now let us discuss the rules for drawing the ray diagrams. So before drawing the ray diagrams, we need to know the rules over here. So here we have a convex lens, so convex lens, and here we have a concave lens. And if we see here, we have two curved surfaces. So this is the first curved surface and this is the second curved surface. And if we assume the first curved surface as, and this as a second curved surface, the first curved surface, if we assume it as a sphere, the center will be on this side. So here we'll be having the center of curvature, so which is denoted as 2f1, and which will be having the focus over here f1. And at the same time, the second curve will be having the center of curvature on this side. So here we'll be having 2f2 and focus f2. And at the same time, if we see for concave lens, so concave lens, if you consider this as the first surface and this as a second surface, so here will be taken as focus f1 and 2f1, and the second surface f2 to f2, and this will be the optic center O. Now let us see the rules over here one by one. So the first rule is when it passes through the optic center. So whenever a light ray passes through the optic center, it doesn't get deviate. So that means it travels in a straight line. So when it passes through the optic center, the refracted ray, that is the light ray, won't get deviate. So it passes in a straight line like this. So that means there will be no deviation when it passes through the optic center. And let us see for the second one. The second rule is when it passes parallel to the principal axis. So when it passes parallel to the principal axis, so this is the light ray which passes parallel to the principal axis. So in convex lens, as it is a converging lens, when it passes parallel to the principal axis, it meet at the focus. That means it converges and meet at a focus. So that means it passes through the focus point. It passes through the focus point. At the same here also for concave, as it is a diverging lens, so when it passes parallel to the principal axis, so here it gets diverged. So it gets diverged, and the diverging line, which is the refracted ray, which appears to be coming from f1, that is, which appears to be coming from the focus. Okay, so that is what, when the light ray passes parallel to the principal axis, it passes through the focus. In this case, concave lens, it gets diverged over here. And the second is when it passes through the focus. So when the light ray passes through the focus, let us see. So when it passes through the focus, it refracts and moves parallel to the principal axis. So that is how the ray moves over here. So it is passing through the focus, so it moves parallel to the principal axis over here. And in this case also, when it passes through the focus, that means it appears to be falling on the focus. So it appears to be falling on the focus. So after refraction, it gets diverged and passes parallel to the principal axis. So this is how it moves for the concave lenses. And the last thing is when it passes through the center of curvature. So any light ray which passes through the center of curvature, it doesn't get deviate, so it passes in a straight line. So that means there will be no deviation, as it acts like a normal over here. Is it clear? So this is these are the rules for the drawing the ray diagrams over here. So the first thing is when it passes through the optic center, it doesn't get deviate. And second thing is when it passes parallel to the principal axis, it passes through the focus. And the third thing is when it passes through the focus, it moves parallel to the principal axis. And the fourth thing is through the center of curvature, there is no deviation, it passes the straight line as there is no deviation. So it acts like a normal over here. It acts like a normal. So these are the rules for drawing the ray diagrams. Now let us see one by one for the convex lenses and concave lenses, one by one in detail. So here predefined, before only I have drawn it here. So let's start drawing the ray diagram. So before starting these ray diagrams, so make sure that you have a paper or a notebook, rough book. You need a scale and you need a pencil. So make sure that all your things are readily so that you can be practiced along with me. So you can pause your video and you can start drawing along with me. So let us start drawing the ray diagrams. So one is the convex lens. So let us start from the convex lens. So before drawing it, so make sure that you have to take the optic center. From optic center to the focus, take it as 2 centimeters, and from optic center to the center of curvature as it is double, so you need to take the 4 centimeters. On this side also you need to take the focus as 2 centimeters, and from the focus, that is from this optic center to the another focus center of curvature, you need to take 4 centimeters. I think you got what I'm saying. So when you draw a principal axis, draw 2 perpendicular lines, and the intersecting line, take it as the optic center, and from the optic center to the focus, take the 2 centimeters on both sides, and from optic center to the center of curvature, you have to take it as 4 centimeters. For example, if you are taking 3 centimeters, that is from optic center to the focus at 3 centimeters, then from optic center to the center of curvature you need to take 6 centimeters, right? So if you take these values correctly, then only you can draw the ray diagrams perfectly over here. Okay, so let us start. That is when the object is at infinity. The first case that we are going is when the object is at infinity. So when the object is at infinity, so let us see how the ray diagram would be. That means it would be parallel like this. So all the parallel rays fall upon the convex lens and they converge at a point. So they converge at a point, so that point is the focus. So here we have the converge at a point which is at the focus. That means the object, the image will be formed. So the image will be formed at f1, that is at the focus. The image which you are getting here is the real image. So the real image means which can be caught on the screen or on a white screen or a wall, and the image which here is inverted, and the size will be highly diminished. So highly diminished means it is a point size image. That means it's a very small and it is a very point size image over here. So this is when the object is placed at infinity, the image is formed at the focus f1 and we get the real image inverted, that means reverse, and here the image which we have is a highly diminished. So this is the first case over here. And the second case, let us see, that is beyond 2f2. So beyond 2f2, that is when it is beyond the center of curvature. So let us see where the image is formed. So here we have to follow two rules, that is the two rules for drawing the ray diagrams. One is, as I told you, draw the two perpendicular lines from the optic center, take it as 2 centimeters, and from to here 4 centimeters, the same as on this side also. So here we have an object, and first thing is draw the line parallel to the principal axis. Draw the line parallel to the principal axis. So when it passes parallel to the principal axis, it passes through the focus. So make sure that your drawing is exactly perfect. So it passes through the focus. And next, second thing is it passes through the optic center, that is the ray which we are having, it passes through the optic center. So let us draw that also. So here we have an object and it is passing through the optic center. Is passing through the optic center. So where the object, the two lines, that is where the two refracted rays are intersected, there we get the image. So here at this point we get the intersection, so here we get the image. So this is the object and this is the image over here. Now when the object is placed beyond 2f2, so the image is formed between f1 and 2f1. So it is formed between f1 and 2f1, and the image which we get here is the real image, that means which can be caught on the screen. And here we have the inverted, that is it gets reversed. See, as if you see, the arrow mark is up over here, but when it comes to the image part, the arrow mark is down, that means it gets reversed, and the size is diminished. So diminished is a little bit small size when compared to here. So see the comparison of the height over here. So both are different, as the image which we are getting here is a small. So that is what we call it as diminished. Now is it clear? Now when the object is placed beyond 2f2, we get between f1 and 2f1. So the characteristics are the real image, inverted, and also diminished. Now let's move on to the another one, that is at 2f2, that is when it is placed upon the center of curvature. So among all the ray diagrams, so this is little bit hard work, so because we need the exact point over here to draw. So let us see. The first thing is we have to draw parallel to the principal axis. So we drawn parallel to the principal axis. And make sure that when you are drawing the lines, these arrow marks are very important. These arrow marks are very important. That is why we call it as ray diagrams. So ray diagrams represents that it should have a arrow mark over here. If there is no arrow mark, then that doesn't represent the ray diagram. So see that exact your point, and this is the refracted ray where it bends over here. And the second line is which is normally passing through the optic center. So it should pass through the optic center. Yeah, is it straight? So it should be passing through the optic center straightly. Here, so this is the ray which passes through the optic center, and here we have an object O, and where the lines are being intersected over here, so that is the image which is been formed. So draw a straight line over there. So when we draw the straight line and draw the arrow mark downward, as we have arrow mark up, so we have arrow mark down over here. So here, what is the position of the image which we get here? So the image is formed at 2f1. So the image is formed at 2f1, and the nature of the image which we get here is the real image, and as it is being reversed, so we call it as inverted. What about the size over here? So the size which we get here is the same size. So let us see whether it is same size or not. So here we have 1 centimeters of height starting from 0. So we have a 1 centimeter of height here, and if you see here also we have 1 centimeter of height. So that means here the size which we are getting is the same size. So when it is kept at 2f2, the image is formed at 2f1, that is at the center of curvature. Here the image, we get the real image inverted and as well as the same size. So this is the ray diagram for when the object is placed at 2f2. And next ray diagram is when the object is placed between 2f2 and f2. So 2f2 and f2, so as usually draw the two perpendicular lines and mention the points exactly, and let us draw the rays over here. The first ray passing parallel to the principal axis, and draw the arrow mark, and next is which passes through the focus. So it should be passing through the focus over here. So it passes through the focus. So this is the refracted ray which passes through the focus. And the second thing is which passes straight to the optic center. So which passes straight to the optic center. Yeah. So this is the ray which passes through the optic center with no deviation. So here we have an object, and the point where it is being intersected is the image over here. So draw a straight line, draw the arrow mark, and the object is placed beyond 2f1, that is the image is formed beyond 2f1. The image which is formed is the real image and it is inverted. Now what about the size over here? Here as it is small and as here it is bigger, so the image has been become enlarged over here. So we call it as enlarged, that is bigger in size. So when the object is placed between 2f2 and f2, the image is formed beyond 2f1, and the nature of the image is we get the real image inverted and enlarged over here. Now let's move on to the another ray diagram. So another ray diagram, the remaining two. So that is when the object is placed at 2f2. So let us see the first ray which passes parallel to the principal axis, and it passes through the focus. So this is the first ray which passes through the focus, and the second ray is which passes through the optic center. So which passes through the optic center. Now are these two lines intersecting each other? So as these two lines are not intersecting each other, that means the image is formed at infinity. So that means at long distance. So at longer distance the image is formed, and the nature of the image which we get here is real image, and it is the inverted image. And what about the size? As if you observe practically, it is highly enlarged. So it is highly enlarged over here. So this is the ray diagram when the object is placed at the focus. And the last ray diagram of the convex lens. So when it is placed between focus and optic center, so the first ray which passes parallel to the principal axis and passes through the focus. So mention the arrow mark, and in this case you need to extend the refracted ray which you get here. The refracted ray which you have, it should be extended. So why it should be extended, that will be know here now. And the second ray which is passing through the optic center, so as it passes through the optic center, so here also these two rays also we have to extend. Now as these two rays cannot intersect at all, but their extended rays can be intersect. So that is, here we have the extended intersection of the two refracted rays. So here we have the image. So here we have the image as the head up. So the image which we get here is the virtual image. That means which cannot be caught on the screen, but which can be seen inside the lens. So the image which we get here is behind the object. So behind the object, or on the same side of the object. We can say on the same side of the object also. And the image which we get here, the nature of the image is virtual image. And if the image is virtual, it is erected, or what we can call it as upright. We can call it as upright also. And the size, when coming to the size, it is enlarged. So the last case is the special case which we use in the magnifying lens. So in the magnifying lens we use this, the property which is behind the magnifying lens is this. So when the object is kept near, we see the magnifying lens over here. So is it clear? So this is the ray diagram between f2 and the optic center O. So this is the image and this is the object. So I think you got clear about the ray diagrams, the total 6 ray diagrams about the convex lens. So at infinity, at a bit beyond 2f2, at 2f2, between f2 and 2f2, and when it is placed at f2, and when it is between f2 and optic center. So we have another ray diagram which is for the ray diagram for concave lenses. So here also, as usually, only 2 ray diagrams will be having for the concave lens. That is, when the rays are passing parallel to each other, that is from infinity. and from infinity, when the rays are passing parallel to each other, so as the concave lenses are the diverging lens, so they get diverged. So that diverging ray also should meet from the focus. So it passes like this, and here we have the dotted ray, that means it appears to be coming from the focus. At the same here also it passes like this and it appears to be coming from the focus over here. So these are the two rays. So the image is formed at focus, that is f1, and the nature of the image which we get here is virtual image and erected, or we can call it as upright also, and the size which we get here is highly diminished. That means the point size image we get highly diminished. So this is the ray diagram for the concave lens, the first ray, that is at infinity. And the second is when the object is placed in front of the lens. So in front of the lens, at anywhere you can keep, at f1 or 2f1, wherever you want, you can place it anywhere, that's your wish. So I'm going to place it here. So this is the object. So here also we have to draw the two rays based upon the rules of here. So the first ray passes parallel to the principal axis and it gets diverged as it is appearing to coming from the f1. This is the first ray. And the second ray is which passes through the optic center. So it passes to the optic center, and as if you can see, there is intersection point over here of the two rays, and there we get the image. So there we get the image, that is I, very small. Now what about the nature? That is, the image is formed between optic center and focus, that is f1, and the nature of the image is virtual as it is forming on the same side of the object, virtual image. It is erected, or what we can call it as upright too, and the nature which we have is the size is diminished, or we can call it as small size also. So is it clear about the ray diagrams for the concave lenses? So we have only two ray diagrams for the concave lenses. One is at infinity and one is at in front of the lenses. So if you observe on the two lenses over here for the concave lenses, the ray diagrams, both for any ray diagram, that is for when the object is placed at any position, we have virtual image, erected, or we can call it as upright, and diminished. So that is for a concave lens, the nature will be virtual image, erected or upright, and diminished image over here. So today we have discussed about the lenses, the types of lenses and its uses, and also the rules. What are the rules for the ray diagrams, and we have seen the rules for drawing the ray diagrams also here. So regarding any doubts about the ray diagrams, you can mail me. So my email ID and my WhatsApp phone number is given down below the link, and you can WhatsApp me at any time. Your doubts will be clarified. And thank you for watching the video. Please subscribe the channel, click the like button, and give your valuable comment. Thank you everyone.